Hi, in this video, I'll briefly explain the homework 5, which we use MPI metrics, the matrix multiplication project, and I'll show some results. So the problem is like to multiply two matrices. The A matrix is n by 32, the size is n by 32. For the B matrix, the size is 32 by n, and the result matrix is like n by n, which is C. So let me enter one of the codes real quick because I just use some like common like same functions for three of the codes. So I'm gonna like talk about those ones real quick, and then I'm gonna like show you what is the differences between those codes. So first, like in here, we have the serial matrix, serial calculations. So it just calculates the um, matrix C. I use that one as a reference result. And here it is like is equal function. It compares the serial results with the parallel results. If it is yes, it turns 1. If it's not, then it turns 0, which is false. And also another one is multiply local function, which is here. So it computes the part of C for a subset of rows in parallel. So this is the like common part for each code. So this code is for called blocking one, which uses the blocking point-to-point communication. It generates rank 0. Uh, Rank 0 generates the full A and B matrices. Let me show you. As you can see here, the rank is 0. And then it sends each process its block of rows of A and the full B matrix using MPI send. Here is the MPI send function. And then sends, and then every process calls multiply local to compute the part of the C. After the partial C blocks are sent back to the rank 0 using MPI send and MPI receive, and rank 0 assembles the full C matrix and compare it to the serial result. So this is what MPI blocking code does. Let's check the other one, collective. So yeah, the same parts is equal, fill random. Fill random, it just randomly fills the A and B and C matrices. So second one, collective, it uses MPI collective communication, rank 0 again, and creates A and B matrices. Then I call MPI bcast. Let me find it where it is. Abort is here. Yeah. MPI bcast is here. So what it does is that it broadcasts B to all processes. And we use MPI scatter to distribute the rows of A. So each process directly receives its local block. And after computing the local part of C, we use MPI getter function, which is here, to collect all C blocks back on rank 0. And this version relies on the optimized collective routines of MPI instead of manual sends and receive. So this is the code looks like for the collective one. And let's check the last one, which is MPI non-blocking. And the third one is, as I said, it's non-blocking, which uses non-blocking point-to-point communication with MPI send and MPI receive. Rank 0 sends A blocks and B to the other processes with non-blocking send, and other ranks receive them with non-blocking receives, followed by MPI wait all. Let's check this MPI wait all. Yeah, that's here. After the local computation, again we use non-blocking sends and receives together the C blocks back to rank 0. In the simple implementation, I still wait for all communication to finish, but it shows how non-blocking API calls can be used. Okay, let's run a couple of cases. Okay, I ran all of the cases, like from starting from N1 to 56 to like 1024 with 4 processors. But let's run a couple of one in here so that I can show you what kind of results are we getting from the simulation. Let's run blocking one. Let's set n as a 10 1024. So these are the errors, which is it's not a big problem. So for the blocking one, when n is 1024, they use 4 processors, and serial time is, as you can see, 0.03, and the parallel time is 0.011, and the speed up is 2.73, and our is equal function return yes, which is, it says the what we get from the serial and the parallel round, like it gives us the same result for C matrices. Let's run, oops, okay, let's run with the other one, with non-blocking one. So for the non-blocking one, again we set n as a 1024. Again we used 4 processors. The so parallel time is, in this time, like again, 0.011, and the serial time is 0.03, and the speed up is 2.75. And again, our serial result and the parallel result are like same. And let's run for the collecting one too. Here's our results. So speed up in this case is 2.778. So we observe higher speed up for when n equals to 1024. So I will be posting the results for different number of n's on my report. So thank you for listening, and I hope you have a good day.